Okay, so in this video, I'm going to be working through problem number 18 on page 139. And there's really no computations involved in this problem. It's just kind of interpreting and understanding what's going on in this graph. So we have a rocket that's being launched. So at t equals 0, the rocket gets launched. And until fuel runs out. Our velocity is still positive. Remember, anything above the axis indicates that velocity is either moving up or to the right. So we're still moving up. So we're moving up more slowly. And then at this point, we turn around. So the rocket starts heading downwards. And then something causes that downward velocity to slow down. And if we read through the problem, this would be the moment when the parachute gets released. Okay. So in part A, how fast was the rocket climbing when the engine stopped? So if we take a look at our graph, here would be the moment where our engine stops burning. Again, because we're still moving upward, so whenever our engine is burning, we're moving very quickly, we're speeding up. And then as soon as that engine stops burning, we slow down, but we're still moving upward. So our velocity around this point is about 190 meters per second. And it's asking for speed, actually. That's how fast, which would be the absolute value of that. So our answer for part A would be 190 meters per second. Part B, for how many seconds did the engine burn? So this one would be tricky. It's tempting to say that the engine is burning perhaps all of this time, or maybe from here to here. But if we take a look at our graph, the engine is burning is only for the first 2 seconds, whenever our acceleration upward is the greatest. So the engine is burning for about 2 seconds, and that would be from 0 to 2. Part C, when did the rocket reach its highest point? What was the velocity then? So we have to think about this. This one, again, is a little tricky. If we're thinking about this in terms of velocity, which is what we're being graphed, what's being graphed here, when velocity is positive, we're moving upward or to the right. So velocity is positive for all of these values. It's positive for all of those values. So for all of these positive values, we're moving upward, even though it looks like we're moving downward. This just means we're slowing down, but we're still moving up. Okay, so we're at our highest point at t equals 8 seconds. And at this moment in time, we turn around. So we go up, 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 and then we start going down. So the velocity at this moment in time would be 0. Oh, I got my units wrong. So this should be feet per second. So the answer in part A should have been feet per second. Excuse me. So in part D, when did the parachute pop out? How fast is the rocket falling then? So we're moving up, 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 and then we turn around and start moving down. Okay, so at this moment we're moving down, and then something causes us, we're still moving down here because we're below the axis, but something causes the rocket to slow down. The speed of its downward fall slows. So at this moment in time, the parachute pops out. So the parachute pops out at about t equals 11 seconds, approximately. How fast was the rocket falling then? So if we look, it's about negative 90 feet per second, but the speed would be the absolute value of that, which would be 90 feet per second. So we can also think about this in terms of the absolute value of velocity. So if we were to reflect this above the axis, then you could just directly get speed. So at this point, our graph would look something like this. Okay? And you could just look at speed directly from that reflection and not have to take the absolute value. How long did the rocket fall before the parachute opened? So we were falling not from here, remember? So here we're still rising. We're rising during this whole period of time, so we're moving upward. We only start moving downward after velocity becomes negative. So it's wanting to know how long it actually fell. So from here to here. So starting at 8 to about 11. So this answer would be about 3 seconds. We fell for about 3 seconds before that parachute opened. Part F. When was the rocket's acceleration greatest? When was the acceleration constant? So acceleration is going to be the slope of this graph. So if we were to sketch tangent lines, the slope of those tangent lines would give us acceleration, which is the derivative of velocity. So I'm going to write that out. This is the slope of the tangent lines. So when is that slope the greatest? I would say it's about right here. Those lines are almost vertical. So they have really, really steep slopes, and their slopes would be the greatest around here. So this moment in time, acceleration is greatest around t equals 2 seconds. Actually, just before t equals 2 seconds. When was the acceleration constant? So when are these tangent lines not changing? And you can see that basically whenever velocity is linear, then acceleration would be constant. So thinking about that in terms of linear, for those of you that are more into, equations, if velocity is some kind of linear equation, mx plus b, then acceleration would be the derivative of that, which is just m, that slope. So anytime you have a linear function, its derivative is going to be constant. So acceleration is constant from t equals 2 is constant from about 2 to 11. Okay, so I just thought that this was a really interesting example to kind of demonstrate all of those pieces that we've been talking about. Yep.